Greetings to one and all. I, Dr. Narpat Sangwa, and Lisa Rossi are here to present the topic Creating Value from Waste, Opportunities and Challenges from the Valorization of Rice Straw. This will be the research agenda for today's presentation: research motivation, literature review, research gap and question, research methodology, case study analysis, results, discussion, and conclusions. There are three research motivations to conduct this study. First one, rice straw is currently burned in Punjab and Haryana to clean the field between harvesting and sowing. Due to the use of combined harvester for collecting rice straw, 40 cm rice straw are left in the field, and there is a short time duration of only 30 days for collection and preparing the field for the next crops. So rice and wheat are two major crops, so only 30 days time period is available to prepare the field for the wheat. So farmers are seeing burning as the cheapest and fastest solution to clean the field. Like in this picture we can see, like there are various fire locations in Punjab and Haryana. These are spotted by red colors. Second, rice straw is burning, having a drastic effect to the environment, health, soil and society. There are various factors which affect the environment due to in-shoot rice straw burning, like global warming, discharge of GHG, destruction of soil microflora, release of particulate matter, and formulation of smoke, especially in beginning of winter, negative impact on soil fertility, cause of accident due to smoke and laser visibility, cause of respiratory problems. And the third research motivation is rice straw valorization can solve the issues of straw burning, industrialization, and social welfare. Although rice straw burning is illegal and government provides the incentive for this, but we can see around 10 million tons of the paddy are burnt in the Punjab in year 2018-19 only. Although in the recent study from Indian Space Research Organization, it is found that the burning events in Punjab and Haryana are decreasing by around 70% in Punjab and 18% in Haryana. So rice straw is a byproduct of rice cultivation, and there are multiple choice to manage this straws, like upstream agri, upstream collection, midstream processing, and end use. Similarly, there are multiple options like in-field option and off-field options. In in-field options like burning, mulching, incorporation, collection, handling, and transportation. And for off-field options like thermochemical conversion of rice straws, like pre-processing, leaching, drying and storage, chopping, then densifications. And then there are agriculture use, energy use, as well as industrial use. In agriculture use, like generation of biochars, composting using the mushroom, then residue which is used for composting, and from like livestock bedding or fodder, again the waste is created which is used as a composting, and then this composting goes to field. From energy point of view, like thermal conversion of the straws are conducted, like combustion, gasification, pyrolysis, and then conduct like heat, electric power, syngas. Similarly, the chemical conversion also there, like biochemical, like anaerobic digester, fermentation, etc., to convert into biogas, ethanol, hydrogens, etc. From industrial uses point of view, like building materials like fiberboard, bricks, and high-end materials like silica, biofibers. So these are the various in-field and off-field options available to use the rice straw as a like value-adding options. So literature findings reveal that the raw material supply chain network design is extremely challenging and require a careful configuration of subsystems. So there are individual or separate research like research on processing and collection technology, research on economics and logistic viability, research on factors affecting farmers' decision, research on environmental impact or GHG emissions. But there is a research gap of integrated supply chain configuration analysis. So the research question raised here are how can supply chain configuration analysis is used to evaluate the valorization of rice straw at scale. And this is the research methodology. So there are 4 themes: rice straw feedstock, technology, market, and value and viability. And these are the decision making variables like in rice straw feedstock, agri waste like sources, quantities, quality, price, moisture content. These are the decision variables. Similarly, in technology, processing capacity, inputs, and product specification and scalability are the like variables. In theme market, potential market, and product demand and product market price are the decision making variables, whereas from theme value and viability like techno-economic and assessment, GHG life cycle analysis, policy scheme, carbon credit, and logistics are the decision making variables. Similarly, like corresponding to these themes, the validations options like feedstock availability assessment, technology processing routes, market analysis, and commercial supply chain evaluation are available. So this framework is adopted for rice straw context, and this is adopted from supply chain network analysis framework by Sarai et al. 2018. Now I invite Lisa Rossi to please continue.
As Narpat mentioned, there are many possible processing technologies and end uses for rice straw, but the question is which one are both economical and scalable? An industrial system mapping approach was used to capture all the possible processing pathways for different end uses. And as you can see in the figure, building and fuel were selected for the case study because of their potential for valorization at scale. In particular, MDF panels from rice straw have been chosen because of the interest of a multinational enterprise in purchasing such panels and the close alignment with the country's strategy to support manufacturing, foreign trade investment, and exports. And finally, also because of the downstream complexity of the supply chain, making this particular case rich to investigate. The results of the case study showed the challenges involved with rice straw as a renewable feedstock. In fact, rice straw is first dried in the field until a satisfactory moisture content is reached. Then it is collected in the form of bales by trained people. And all of this needs to be done in just 30 days. The bulkiness of the bales makes the transport difficult, and therefore distance is needed to be minimized to below 20 kilometers to ensure economic viability. The bales are also stored in stacks, covered in tarpaulins, and then kept at a distance for vehicles to pass and to reduce fire hazards. Therefore, a farmer-producer organization that can coordinate the collection and arrange land for storage and processing inside the cluster appears favorable to optimize logistics and minimize the issues involved with the challenges of collecting rice straw. Two technology manufacturer companies were considered based on both processing capacities and demand requirements. These two technologies are continuous pressing, that is more industrial and scalable, and daylight pressing, which has a smaller capacity. As you can see, daylight pressing was chosen because of it more closely meets the predicted demand requirements and also requires lower investment, which is more appealing due to the risks involved with this process. IIT Roper has been conducting tests with the support of the technology manufacturer company in order to demonstrate the technology readiness with the local rice straw from Punjab. As you can see, the images below show the different steps of the manufacturing process. So first, the stored rice straw is screened, chopped, and milled in several stages to obtain 40mm pieces. If the moisture content is satisfactory, the straw is sprayed with MDI resin in a rotary drum blender and then placed into a mold, pre-pressed with a wooden plank, and then hot pressed in an hydraulic press at 165 degrees Celsius. Finally, the pressed boards are left to cool at ambient temperature and cut to appropriate dimensions. The global furniture market is estimated to be $600 billion. And the Indian market is predicted to increase significantly due to the increase in upper middle class population. Currently, 90% of India's demand is met by imports, but top furniture players are willing to source from India, even though there isn't sustainably sourced wood available in the country. But there are large quantities of rice straw, highlighting its potential as an alternative to wood to meet the predicted furniture demand of 10,000 meters cubed per year in the north of India. The overall configuration for producing MDF boards from rice straw using the compact technology was evaluated to determine its economic viability and environmental benefits. The results show that the depreciation and raw material costs have the greatest impact. So incentives from the government are needed to make the investment more attractive. In this case, farmer producer organizations can secure 35% of subsidy on machinery, making the price of boards competitive in Europe with an investment of approximately 1.5 billion rupees for 2 compact lines, which is equivalent to 20 meters cubed per year at a payback of 5 years and an internal rate of return of 26%. The case study results and analysis revealed 2 stages for identifying and designing a supply chain from renewable feedstock availability instead of demand-driven. The first layer is more strategical and consists of geospatial analysis to identify clusters of available waste, then industrial mapping to evaluate potential pathways that are technologically ready, and uses are then selected based on market value and volume requirements, and a preliminary configuration is identified based on the alignment with government and policies. The second layer consists of a supplier, technology, and market, and techno-economic environmental assessment at a deeper operational level to test the configuration and determine its viability for implementation. A third layer is being explored, looking at partnership configurations to further enrich this framework and support future supply chain designs for other renewable feedstocks. To conclude, this project applied the supply chain configuration analysis in a new context, which led to the development of a refined framework for the design and implementation of configurations that are driven by the availability of waste. The project also demonstrated the selected supply chain configuration is economically viable, with a payback of 5 years and an internal rate of return of 26%. It is also environmentally beneficial, with an approximate carbon reduction of 3 tons of CO2 equivalent emissions, and that the MDF panel price could be competitive in Europe with government incentives on machinery. Thank you for listening.